Mm. Okay, so this is week 9, lecture 2. And what we're hoping to do is today I want to introduce you to the ideas of field theoretic renormalization group. We're not going to go into any details. My goal is simply to give you a skeleton of what the idea of the theory looks like. And to do it properly would require a whole course. The detailed stuff is in chapter 12 of my book. If those of you who may be interested to learn about it, I'll be happy to tell you about that. What I want to do now is I want to just explain the logic of it, because it's the logic that frequently is where people get stuck. So what we did last time was we did a dimensional analysis of Landau theory. And what I showed you was can you open the back door, please? And put the stopper in so that people can come in. Okay. There's other people coming. Yeah, thank you. Right. So what we did was I showed you how we can rescale the Landau theory and transform the expression of the partition function into a path integral, a functional integral, which we haven't really described in detail how we even do it, but it doesn't matter. And the point about that was that the path integral, or the functional integral, was just a function of a single variable, which I've called u naught bar here. And that variable comes in the following way. By doing the rescaling that we introduced last time, we have a Hamiltonian, which I called H naught, which is the non-interacting Hamiltonian, which you can think of as being fields that are non-interacting. Everything is exactly diagonalizable. And as we'll see, the partition function with just H naught is exactly solvable, and we can all do the integrals. And you learned how to do the integrals on your mother's knee, so you can all do those. The hard part is the interaction part, the part that comes in with terms of order, the order parameter phi to the fourth, and they're multiplied by this single quantity u naught, which we got by doing rescalings. And what we discovered was that parameter u naught bar scales like t to the power d minus 4 over 2. And that tends to infinity as t tends to 0 for d less than 4. And so we concluded that there was no small parameter that was usable in the problem of phase transitions, and that's why this problem was so hard. So then we had solved this problem before by doing block spins in real space, and we saw that method worked pretty well. It gave us anomalous exponents that were reasonable compared to the exact solution by Onzaga, but it did that. It was very laborsome, and it required a lot of irrelevant variables at the Gaussian fixed point, which have to be taken account of and computed, and then in the end ultimately don't matter. But you still have to include them in the calculation. So we're looking for something that is more streamlined, and what really gave a huge supercharge to the community studying phase transitions in the normalization group was the invention of the epsilon expansion by Wilson and Fisher, which was published in Phys Rev Letters in 1972. The paper was called Critical Phenomena in 3.99 dimensions. And the basic idea was to use as an expansion parameter the dimensionality. And the idea was that we know that above 4 dimensions, the phase transition problem has exponents and so on, which are just those of mean field theory. And so they're trivial in that sense. But when we get the scale interference phenomena below 4 dimensions. And so the idea was, well, why don't we use as a small parameter the distance between the dimension that you were in and 4 dimensions where things become easy. And we'll see that is a viable strategy. Now, what we're going to do is we're going to do the thing that makes this technically very attractive is that we're going to do the calculations in momentum space rather than real space. But that's the only conceptual change. I'm going to try to emphasize the similarities with what you already learned in the real space renormalization group, which is very intuitive. So let's go back to what we did in the real space renormalization group. So that's shown at the bottom of the right-hand panel there. So we divided the system up into these block spins, And then we had degrees of freedom that were the short wavelength degrees of freedom within each block. And then what we did was we integrated those out and worked out what is the effect perturbatively of the interactions between blocks. And we did that last week, and it was a lot of calculation, but we went through that. And conceptually, it was an exact realization, but an improved version of Kadanoff's block spins. So now what we're going to do is we're going to take our fields, our spin fields, and write them in K space rather than in real space. So then what's going to happen then is when we have a block of size L, remember L is the factor that the block size is bigger than the lattice spacing. So what that means is we're going to be imagining that we have a system with a lattice or some cutoff at high momentum, which I've called lambda in the top picture here, and the analog of the spins within each block. So here are the spins within each block, and these we call the sigmas. And those are then high wave number modes, and so those occur here. And if the blocks have a size of the lattice spacing times L, then that means that we're taking momentum variables, momentum states, which go from lambda to lambda over L. And so what our strategy is going to be is we're going to try to integrate out these high wave number modes, just as in the real space version, we summed over the spins within each block spin and eliminated those and just got now an effective Hamiltonian for the block spin variables. So that was the idea. So we're going to do that, and there's two distinct parts of it, and they're not really to be confused. So one is the epsilon expansion. So that's one technical part of how we do the integrals, how we do the Feynman diagrams that we're going to end up with, which you'll see. So that's really not the most important part. The most important part is how we do the coarse graining. And I want to explain to you, first of all, how we expect this to be, to solve the problem that we're trying to solve. So let me give you now an outline of this. So the basic idea that we're going to pursue is this. So when we're in D greater than 4, we expect that mean field theory is okay. Okay, and that means that Landau theory is okay. And that means that the interactions between the fluctuations can be ignored. Okay, and we saw in the homework, and we saw when we did mean field theory, mean field theory involves removing the interactions between fluctuations. Those interactions are represented by the fourth order terms in the Hamiltonian. So these terms here, oh no, not that. These terms over here are the interaction terms, and those are the terms that we're going to ignore in mean field theory. That's what mean field theory does, and it works above 4 dimensions. So that's the first thing. So then what that means is that when we do the Landau theory, all we have to do is compute integral ddr going back to the physical units, 1/2 grad s squared plus 1/2 r naught s squared. That is the only part that we have to do. So this has ignored the fluctuations. And this thing is a Gaussian integral. And we can do it exactly. And I'll show you how to do it. It's not hard to do. Okay, so that means that if you think about the coefficients that come into Landau theory, so Landau theory in general has R, or R naught, as we called it, the coefficient of the quadratic term. r s squared plus u s to the fourth minus h times s. Those are the interaction terms. So what we expect is that we can compute the fixed points will be r star is equal to 0, u star is equal to 0, and h star is equal to 0. So that's going to be a fixed point that corresponds to the Gaussian theory. So this just says that T is equal to Tc, U star is equal to 0 because we've set the fluctuations equal to 0 because we are in D greater than 4 and mean field theory is exact, and H star is equal to 0 because we're interested in the case when there is no external field. So we expect that, so this is what we expect. Okay, so that's the point. Now, what's going to happen is when we go to D less than 4, we know that this fixed point can't be true. And the reason is because we know that there has to be a U star that is not equal to 0, meaning that the fluctuations are important. And so there's going to be a fixed point value for the fluctuations, the coefficient that controls the fluctuations. And that coefficient then is not going to go to 0. It's not going to be a free non-interacting theory. So we know that that can't be true. In fact, it also turns out that R star is not equal to 0. In other words, the transition temperature that you estimate in mean field theory actually gets changed as a result of the fluctuations. Okay, so, but H still stays 0. So now I want to tell you about what that fixed point is. So this fixed point, so what that means is that there is a new fixed point, and that fixed point is called the Wilson-Fisher fixed point, which is known as the Wilson-Fisher fixed point, in addition to the Gaussian fixed point. And what our idea is, because we're expanding in dimension, then what we will expect is that if we're in a dimension that's near 4 dimensions, we would expect that that fixed point will be of order epsilon. In other words, as I go towards 4 dimensions, we know that the U star is going to then go to 0. So therefore, if we're not in 4 dimensions, it's not unreasonable to expect that, that therefore U star would be a number of order epsilon. And so that's what we would expect. And therefore, we're going to try to calculate that. Once we've calculated that fixed point, once we've identified this and understood it, then we do the same thing we've done before. We look at the linearized renormalization group transformation about that point, do the calculations, compute the eigenvalues, and work out the critical exponents. So the first step then is to construct that fixed point. So now I want to give you a plausibility argument for everything that I've said. So this is just so that before I do the actual calculation and you see what a mess it is, at least I want you to understand where it comes from. So remember that we worked out last time how U naught scaled with space when you're near when you change space. So we worked out the dimensions of U. Remember, I made a mistake in the class. I forgot to do a rescaling step, which Gregory pointed out, and we did that and discovered that. But I worked out what the dimensions of this thing were, and so what we know is that under a renormalization group transformation, under renormalization group transformation R of L, what we know happens is that U naught transforms to U prime, and because U has dimensions L to the 4 minus D, this is going to go like L to the 4 minus D times a U naught. And so that is then L to the power epsilon times a U naught. So that's what we would naively expect. Of course, it's not correct. And the reason it's not correct is that we've only done naive dimensional analysis, and we haven't taken into account the other terms, and we'll see why that matters in a little bit. So So what that would say is, if U naught prime goes like L to the power epsilon, remember we talked about the continuous renormalization group, where you take the size of the block spin, which is L, and then you write L as 1 plus epsilon, and then you work out 1 plus S, and then you work out a continuous renormalization group. So in the continuous renormalization group, we define a variable S is equal to the logarithm of the scale L, and then we get the renormalization group recursion relation for U, the quartic coupling constant, as a function of scale S. And that equation is going to be du S by ds is equal to epsilon times US. Okay, so remember, all I've done is I've taken this formula on the left-hand panel, made L infinitesimal, then taken the limit, made it a continuous scaling of U, and because I've scaled it with log L, then the epsilon then comes down and multiplies it like that. And so that is what dimensional analysis tells us. Now, so this is, if you like, the dimensional analysis version of the normalization group, which has involved no calculation, just the statements that we know from dimensional analysis. Now, what comes next? So in the normalization group, the extra step that we do, compared to just naive dimensional analysis, is that we integrate out by wave number modes, and they interact. So we're integrating out k values greater than lambda over L, just as I showed you on the left-hand panel here. So we're integrating out these high wave number modes. And when we do that, we're going to get, because of the interaction between the fluctuations, then that will change the recursion relation from dimensional analysis. So what do we expect to happen? Well, we have to, of course, do an honest calculation, but what you might say is, well, if we have dus by ds is epsilon times us, where we're not including the interaction between the fluctuations, then when we include the interaction between the fluctuations, I suppose what's going to happen is there's going to be another term, which will be some number times us squared, and there might be higher order terms, US cubed, and so on. So it's reasonable to expect that the next correction is going to be something of order US. And if A is positive, if A is positive and the sign is negative here, which of course remains to be seen by doing a real calculation, then that would say that the fixed point is going to be dus by ds is equal to 0, which means that US, the fixed point of the quartic coupling, is then going to be epsilon over this number A. And so again, that's why we think that there's going to be a fixed point, a non-trivial fixed point for the interaction between the fluctuations, the quartic term, which will come from integrating out the short wavelength degrees of freedom. And naively just saying, well, if you just do nothing, you'll get a linear term in the recursion relation, and now there's going to be these nonlinear terms, and so the lowest order one is going to be of order like this, and will lead to a fixed point of order epsilon. So that all remains to be seen, but that is the strategy. So the next thing that then we want to be able to do is we want to understand how to compute this precisely. So that is the overview. So we want to compute this fixed point precisely. And what we want to do then is then do the linearized RG about what I'm calling the Wilson-Fisher fixed point, and then get the RG eigenvalues and give the critical exponents and all of those things are going to be done to order epsilon. So most people who have got tenure in theoretical condensed matter physics may have done at some point in their lives an order epsilon renormalization group calculation. People who are real experts might have done order epsilon or order epsilon squared. People who are absolutely real experts on all of these things can take these calculations using automatic numerical or symbolic computation to high orders like 7th order, 8th order, something like this, and really try to get very accurate estimates of critical exponents. Okay, so the way we're going to do this is we're going to start with the order epsilon to the 0 part. In other words, what we're going to look at is the so-called Gaussian theory. And I'm going to just spend a little bit of time going through how we write down what this functional integral that I've so far resisted telling you what it actually is. And so we're going to do that. We're going to show how to write down a functional integral in a constructive way. Now, in the homework, you actually saw how to do that when we did the Hubbard-Stratonovich in the homework, and you saw how to write down a functional integral as basically a big multiple integral. Now we're going to do the same thing, but the difference is that this time it's going to be in momentum space. So let me give you a reference here. What we're going to follow is the discussion roughly around page 155 of my book, which is the definition of Fourier components. So I'm going to quickly go through that, and then we're going to write down the Gaussian model in Fourier space. So let's get started then with step 1. The Gaussian model. So the thing we're looking at is the effective Hamiltonian, which is I'm going to write in this form: integral ddr. I'm going to write it as 1/2 rad s squared plus 1/2 r naught s squared. So that's going to be the Hamiltonian that I want to solve. It's a quadratic Hamiltonian. All right, let's write it down in Fourier space. So what we're going to do is we're going to define S of R is equal to 1 over V, the volume of the system, sum over K, e to the I K dot R, and then S of K. And I should really put hats over the Fourier variables, but I'm sure I will forget to do that. And then, so that's the discrete Fourier transform, and the S of K are defined to be the integral over the volume, integral d dr, S of R, e to the minus I, K dot R. So that's the definition. So the first thing I want you to note is that we're doing this in a finite volume. And we will usually have to say what the boundary conditions are since it's a finite volume. So we will usually use periodic boundary conditions. So I told you this is a discrete Fourier transform, because if you have a finite volume, then as you know, the allowed K modes are not, it's not a continuum, they're quantized in units of 2 pi over L, where L is the linear dimension. And so we're going to have to write down what are the precise K modes. And I'm going to do that for you in just a minute. Okay, so that's just the definition of Fourier transform. And I want to do a simple check that this is correct. And so the check is what I call the resolution of unity. And all that means is if I take my definition of S of K, which I have on the second equation above, and I substitute it into the formula for S of R, I should end up with S of R on the right-hand side. Okay, I should end up with a formula S of R equals S of R. So let's see if that works. I'm going to go through this just because I want to make sure everybody here understands the basic manipulation and avoids a trap that a lot of students run into. So let's just try the resolution of unity. So what we're trying to do then is check that if we substitute S of K into the formula or S of R, then it is consistent. Okay, so let's have a look at that. What do we do? So the idea then is we take S of R is 1 over V, sum over K, the allowed K modes. I'm going to write down explicitly what they are a little bit later, but you all know this. And then what we're going to do is we're going to put in the formula for S of K, and the formula for S of K is just the one over here. So let me put that in. So we're going to put in the integral over V d dr S of R e to the minus I K dot R. Okay. Stop me if you see me writing down something that's wrong.
You have to change K in the integral to K prime.
No, but you're on the right track.
Yeah, basically when you multiply e power ik dot r and e power minus ik dot r, the K can't be the same. Because
Well, so I know what you're saying, and I know where you're thinking, but think about it carefully, okay? What I'm doing is I'm saying you tell me what K is. It's a dummy variable. So I do, if I'm substituting this S of K in here, this is a dummy variable. So I have to call it K. I am starting over, but you're on the right.
It should be not R, but R prime.
Thank you. Thank you. The mistake is it should be R prime, not R, because R prime here is a dummy variable. And so, you know, it's not the same R as it is on the left-hand side. So this thing has to be R prime, this has to be R prime, and this has to be R prime. Okay, so the K, so you were right. I know what you were thinking, but you were memorizing what you've seen somewhere else, but not thinking about where the actual problem lies. So do you understand that now? Yeah. Okay. So that's the trap. So we have to make sure that the dummy variable is correctly identified. So the K is correct, okay, because that's also another dummy variable. All right, now let's do the calculation. So now what I'm going to do is I'm going to just simply rewrite that as the integral d r prime s of r prime. And then what do I have left? Well, I have 1 over v, the sum over k, and then e to the I, k dot r minus r prime. Because it is the same k. And I can't take that last r prime with the other r primes because it involves k, and I have to do the integral over k. So now we know that this the left-hand side of this has to be S of R. So let me squeeze in an S of R in here. I know it's terrible. Hang on, let me just do this. Okay. Just had an earthquake. All right. So we know that that has to be true. Okay, now put your hands over this so you don't look at this thing. Okay. You know S of R is equal to the integral of R prime S of R prime times something. What does that something have to be?
Delta.
It has to be a delta function. Exactly. So what we know is that this has to be, the only way this can be true is this is integral d r prime S of R prime times delta of R minus R prime. And so what we've just learned is that if that's true, then that implies that 1 over v sum over the k modes e to the I k dot r minus r prime is equal to delta of r minus r prime, and this is a Dirac delta. Okay, so and why is it a Dirac delta? Because r is a continuous variable inside the volume. So what are the k vectors? The k vectors have to be discrete. And if I think of the volume as being like this, so there's my volume, then I have that V is equal to L cubed, and K has to be discrete, and that means that the K values have to be 2 pi over L times in integers in 1 and 2 up to however dimensions I have, where the n's are integers. Okay, so let's see if that makes sense. So we can ask another thing, which is important to remember, and is more or less the only thing that you need to remember if you're going to do solid state physics. So the next question is, does this make sense? In the continuum limit. And what do I mean by the continuum limit? What I mean is that I take V goes to infinity to get the thermodynamic limit, and then my sums over states become integrals over k's. So in that limit, then we have sum over k is going to be replaced by a integral over k, and there has to be a number that comes in here, and this number is the density of states in k space. So let's let me write it down. Density of states in k space. All right. So what do we mean by that? So my k values is, as I said, 2 pi over L. Let's just do it in 3 dimensions: nx, ny, nz. And these are integers. So then if you think about, well, how do I turn a sum into an integral? Well, the simplest thing is just to say, well, turn the sum over k into an integral over k. So you might then say that means the integral dk is then going to be 2 pi over L, but there's d dimensions, so that's going to be raised to the power d, and then I'm going to be summing over n, and so the sums over n are going to be integrals dn, where n are the integers, and so what that means is if I compute the density of states, so the density of states is the integral the dn, those are just integers, so that's just equal, well, this is just 1 in each dimension. So therefore, the factor that comes into this integral is then the transformation between dk and dn is then dk is equal to 2 pi over L to the power d dn. And so the density of states, so therefore the sum over k then becomes integral, well, v over 2 pi to the power d times the integral d dk. So if you have seen that for the first time, then you should definitely check this. So all we've done is turn it's the sum over n into an integral. So this thing then just goes, this term here just goes over to here, and that's how and we say that this thing here is basically equal to the sum over the k states. Okay, so that's the density of states in k space. So then let's see how that applies to our resolution of unity. So what I've got then is 1 over v sum over k e to the I k dot r minus r prime. So that's the thing that we had over here that we guessed it must be. So that's our guess over here. And now let's see if we can check that guess is true. So now we're going to take this sum and we're going to write this as 1 over v. Then we're going to turn the sum over k into v over 2 pi to the power d. Then replace that by integral d dk, and then times e to the I k dot r minus r prime. And this then, and we're going to take this in the continuum limit as v goes to infinity. So this is then going to be, the v's cancel out. So I'm going to get 1 over 2 pi to the d, the integral d dk e to the I k dot r minus r prime. And this is going over all space, but it's all k space. Okay, and if you remember what the Dirac delta function is, you'll see that this thing is then just equal to the Dirac delta function as a function of r minus r prime. Because remember, delta of x is equal to 1 over 2 pi integral d dk e to the I, so in one dimension, which is how you learnt it originally, is integral dk e to the I kx, going from minus infinity to plus infinity. So, okay, so this statement over here, this resolution of unity was indeed correct on the left-hand side. Okay. So what we've just learned then is that there's in this picture we have one point or k state in k space per 2 pi over L cubed volume in k space. Well, another way of saying it is just to remind you, the integral, the measure d dk is then just 2 pi over L to the d dn. Okay, so that's what we just did. All right, now let's see how this applies to the partition function.
Should it be R space? 1 point in K space for 2 pi over L in K space.
Yes, well, that 2 pi over L cubed is not a volume. It has dimensions of 1 over volume.
Yeah.
Okay. All right. So now let's carry on. So how many of you have seen these sorts of manipulations in K space and Fourier transforms before? Some of you have. Okay. Some of you. And how many of you could have done it without me explaining it? Maybe. Okay. All right. I know you've seen it before, and then by now I want to make sure you've had it explained to you, hopefully in a crystal clear way. Okay. So now let's go back to the partition function. Remember, all we're doing is the Gaussian partition function. So we're looking at our Hamiltonian is 1 over V, the sum over naught is less than K, is less than lambda, and then 1/2 S of K squared times R naught plus K squared. So that's our Hamiltonian in K space. How did I get that? Well, I took our original Hamiltonian, which we have over here, step 1 on the left-hand side, and I just did the Fourier transform and used Parsifal's theorem. And the point is, it's diagonal in K space. Okay, there's only one sum, not two sums. It's diagonal in K space. That's why people like K space and like momentum space. Okay, so it's diagonal. So then, if I write down the partition function is the trace over the degrees of freedom of e to the minus the effective Hamiltonian. And I'm going to write down this trace. Well, I can do it as a trace in real space, or I can do it as a trace in K space. So this is then a trace over the S of K modes, e to the minus the effective Hamiltonian. And so that is then equal to the integral from minus infinity to infinity, the product over naught is less than K, is less than lambda, d S of K, e to the minus the effective Hamiltonian as a function of S of K. Like that. Okay, so let's have a look at what we have here. First thing is that S of K is here and it's being integrated out. So it's our dummy variable. And the answer, once we've done that, is just going to depend on the parameter in the Hamiltonian, which is R naught. Okay, so that's the first thing. The other thing is that you've heard me say this before, and I'm going to say it again. I want you to remember this. Space is just a label. Okay, so sometimes people get confused when they're doing field theory. How do we do these functional integrals with spatial extended fields and things like this? So the answer is space is just a label. And so that means that K space is just a label. So you can see here that the states are labeled by K over here, and we are summing over all of those K values. So it's a dummy variable, and it just is a label on the degrees of freedom. Okay, so you don't have to worry about what that means. That's what we're doing. Okay, so that's what we're doing as a functional integral. So how are we? I want to now talk about a normalization. So the next thing is the normalization of the order parameter field. So when we did this in real space, we did a very clever trick. We started off with SI is plus or minus 1, and then we did our renormalization group recursion relation. We had a block spin variable, which we had constructed in such a way that it was also plus or minus 1. So it had the same range of values as the original field. So then now we're doing this in K-space, so now we have an interesting problem. How does S of R or S of K change with scale? So we're going to need to figure that out. And what we want to do is we want to renormalize it. And I'm going to write it like this: renormalize the variable S of R after each scale transformation. So that we get our effective coarse-grained Hamiltonian looks like the original one, looks as much like the original one as possible. And the reason we want to do that is because we want to make it easy to see how the coupling constants transform, to make it easy. So our coarse graining step will involve coarse graining, integrating our degrees of freedom, and then literally changing the normalization of the order parameter field so that it looks like the original Hamiltonian. Can you see it okay?
Yeah.
Okay. All right. So let me explain the renormalization. So why did I call it renormalization? So what we're going to do is after each coarse graining, we insist that the coefficient of grad S squared is equal to 1/2. Okay, so that's our renormalization. So remember, going back to the original Hamiltonian, let me just go back a couple of slides. Here we are. If we look on the left-hand panel, so look over here where I'm writing. So we set it up in such a way that the coefficient of the gradient term is equal to 1/2. And what we're going to do is do the same thing. We're going to make sure that we change variables after we've done the coarse graining in such a way that in these transformed variables, the gradient term looks like a half gradient S squared. It's not the only way to do it, but that's the way that we do it in practice. When we do that, then, once we've rescaled everything, then we can read off what R naught has transformed into. And that's how we're going to do it. So that's not the only way to do it, but that's what we're going to do. So that's the first thing. The second thing is that we integrated out lambda over L is less than K is less than lambda. Remember, I wrote this down at the beginning of the class. Here we are. On the left-hand side, the high wave number modes are the ones that we've integrated out. So what that means is, in order to make the effective Hamiltonian comparable to the original one, after the coarse graining, we need to rescale space so that the transformed k vector is now going to be naught is less than k prime is less than lambda. So we're going to have to do that as well. And so how do we do that? Well, we already know that the rescaling of space is just going to be, we go to a new space, which is R prime is defined as R over L. And then in that new system of coordinates, then K will then go back to being between naught and lambda. And so this way, we get our original Hamiltonian defined on the same variables and the same spatial dimension as the original problem. Now, why is this non-trivial? Well, this introduces an interesting problem. This rescaling is non-trivial because we're rescaling in space. But remember that when we worked out last time the dimensions of the order parameter field, we saw that that had dimensions of L to the power 1 minus d over 2. And so when we rescale space to get our k space to be between naught and lambda, just like the original problem was, the order parameter field is also going to transform. So we've got two things happening. One is a transformation of scale, just because we've coarse grained and we want to get the original problem back to where it was, so we can then iterate the transformation. The other is because the order parameter has non-trivial dimensionality, then it changes. And then the last thing is the interactions between the degrees of freedom on small scales will then also cause changes into the renormalization group recursion relations and introduce new terms. So there's a lot of things going on here in all of these things. So when we call it renormalization, we literally are, after the coarse graining step, we've thinned out our degrees of freedom. We've got rid of all the ones on the left, if you look on the left panel, we've got rid of these ones here, these have now gone. And then what we want to do is rescale K so that this lambda over L now becomes the original lambda. That's what we're doing. So we're literally renormalizing space and we're renormalizing the order parameter. That's where the word renormalization comes from. Gregory, you wanted to ask a question?
I'm just wondering if it is always possible to have a transformation such that our Hamiltonian has the same form.
It won't have exactly the same form. So you might start off with this and then find that you generate new terms, just like we did in real space. Okay, and then you have to ask, are they relevant or irrelevant? So it's not always guaranteed that it will. But what we will be able to see is that beyond fourth order, we don't need to include any other terms. All right. So yeah.
Rescaling of space, consequence of RG itself. Why?
Rescaling of states is because we removed, go back to this picture here. Okay, so go back to this picture. Right? So we integrated out these degrees of freedom. So that's the coarse grain. That's like putting everything into block space. But now our spatial variable now goes over a different one in the K space. And we want to be able to read off the renormalization group recursion relation. To read it off, we need to say we have this integral on the left-hand side, the same integral on the right-hand side, but different coefficients. So we need to get all the coefficients to be the same. And that's why we have to rescale the space. We rescale space because we've done the coarse grading, and then non-trivial things happen because of the dimensionality and the interplay between the short and long wavelength degrees of freedom. Okay. Okay, so now let's go through how we do the calculation in a bit more detail. So the next thing we want to do is how we define long and short wavelength degrees of freedom. So what we're going to do, keep your eye on the picture on the left-hand panel. I'm going to define SL prime of K is the same thing as S of K only when naught is less than K is less than lambda over L. And then I'm going to call the sigmas, sigma L of K is going to be the S of Ks, which are in the range lambda over L is less than K is less than lambda. So those are the long and short wavelength degrees of freedom. So we can write, therefore, that S of R is the integral from naught to lambda over L dk over 2 pi to the d, S of k e to the I k dot r plus the integral from lambda over L to lambda dk over 2 pi to the d, S of k e to the I k dot r. So that is how I'm breaking this thing up, and then that means that I can think of this thing as being the SL of R, and this thing here is the sigma L of R. And if you look at the analogy with real space renormalization group, so this thing is like the sigma I, and this thing is like the SI. Okay, so now let's write down our Hamiltonian in terms of these variables. So if I do the Fourier transform, it looks like this: 1 over V sum over naught is less than K is less than lambda over L, 1/2 SL prime squared times R naught plus K squared plus 1 over V, the sum from K over L is less, lambda over L is less than K is less than lambda, and then 1/2 sigma L squared R naught plus K squared. And so I can think of the effective Hamiltonian as a effective Hamiltonian for the S degrees of freedom, the long wavelength degrees of freedom, and a effective Hamiltonian for the short wavelength degrees of freedom, which just depends on the sigmas. And when I write down my partition function, all I have to do is say, well, the partition function is the integral from of ds e to the minus h effective. And so what's that going to be? Well, I've got 2 degrees of freedom, the s's and the sigmas, so I write those down separately. So this is naught is less than k is less than lambda over L d SL of k, and then product over lambda over L is less than k is less than lambda d sigma L of k, and then e to the minus hs minus h sigma. All right. So what you've just seen is that the measure in the functional integral in K-space factorizes into the part that depends on the long wavelength degrees of freedom S and the short wavelength degrees of d sigma. But because in the quadratic order, the Hamiltonian just ends up being a sum of the 2 degrees of freedom, the long wavelength and the short wavelength degrees of freedom, they just come into a Hamiltonian like this, like I've shown you over here on the left-hand side. And so that means that this factorizes, and the measure that also factorizes. And so what we end up with is that the partition function, which depends on one parameter, which is R naught, is equal to the partition function for the long wavelength degrees of freedom times the partition function for the short wavelength degrees of freedom. And we saw that in real space too. Remember when we did the real space renormalization group, what we saw was that we got a term which we called Z naught of K raised to the nth power. M was the number of block spins in the system, and we worked out the partition function for one single block spin with just 3 spins, and then we raised that to the nth power. That was the partition function for the short wavelength degrees of freedom. So this term here is analogous to the Z naught of K to the nth power from in the real space renormalization group. Okay, so the point is that in the Gaussian theory, the partition function factorizes into a part that is long wavelength times a part that is short wavelength. That's the part that is short wavelength. And what that means is that both of those integrals can be done, exactly. So that's the first thing, that's great. The second thing that's great is each integral can be done exactly. Okay, so let me just make sure that you can see why that's the case. Look on the left-hand panel here. And look at, say, this term over here. You can see that the variable is a half S prime squared multiplied by a function of K, R naught plus K squared. The variable that you're integrating is S. So I'm integrating e to the minus S squared times something. So every integral there is just simply a version of every integral is a version of the integral minus infinity to infinity dx e to the minus a x squared. Okay, and you learned what that integral is. What is that integral? You learned this on your mother's knee. Yeah. So if you know that integral, then you know everything you can do everything in field theory. Okay, so what we have to do is now take the product of these two things. So there's a complication that I want to explain. So if we're going to do this correctly, we have to remember the following thing. We start off with an integral. S is a real variable. When we do the Fourier transform, then we're going to get a complex variable. Okay, so if I write down what is the measure, when I write down d sigma L of K mean in, say, if you look here on the left-hand side, I've got these product over integrals. D sigma L of K sigma of k is a complex number which has real and imaginary parts. So this is equal to d times the real part of sigma L of k times the imaginary part of sigma L of k, and the same thing for anything else. So just make sure you know how to think about that. Well, you know that if I have the integral d to x, where x is a two-dimensional vector, then that is equal to dx dy, where x is equal to x and y. So here we have z, we have dz is equal to dx dy, where z is a complex number, x plus iy. So if I have an integral over a complex variable, I'm integrating over the real and imaginary parts. Okay, so now let's do the integral. And the one I'm going to do is I'm going to do the sigma integral. So let's have a look at what is z sigma. This is the integral of the product over lambda over L is less than K is less than lambda, d sigma L of K e to the minus H sigma. And H sigma is what we have on the left-hand page. So this is the product of the integrals. Lambda over L is less than K is less than lambda, d sigma L of K e to the minus H. I just wrote this down. Sorry. Let me backtrack. Sorry, I lost my place. This is equal to then, because everything factorizes here, this is just the product from lambda over L is less than K is less than lambda times the integral from minus infinity to infinity d sigma L of K e to the minus 1 over 2v sigma L of K squared times R naught plus K squared. Okay, look what I did. Because the Hamiltonian for Z sigma, the Hamiltonian for Z sigma is this thing over here, and it's just the sum of a bunch of terms which depend on K. So when I write it in the partition function, they just are a product. So when they're a product and the sigma is a product, then I can take the product outside, and inside this is a number which is going to end up, this is going to be some thing that this is a number that depends on K. And it depends on R naught. The sigma is a dummy variable. And so then we have to, once I've got that number, then I have to multiply it together over these ranges here. The K is just a dummy variable, and then I work out what it is. Okay, so let's now work out what that number is. So remember over here, integral dx e to the minus ax squared is root pi over a. So that means that is equal to root pi times a to the minus a half. A to the minus a half is e to the minus a half logarithm of a. Right? Okay. So therefore you can do in your head what is Z sigma. So therefore Z sigma is going to be e to the 1/2 the sum over lambda over L is less than K is less than lambda times the logarithm of 2 pi over V R naught plus K squared. And that just comes from what I did on the left-hand side.
Treating sigma of k and k as independent variable.
How do I do what?
Treating sigma of k and k as independent variables because sigma of k is some polynomial of k.
So remember, well, if I have sigma, let's suppose I have a complex number, e to the minus z squared, which is what I have over here. Okay, so that is equal to e to the minus x squared plus y squared, which is e to the minus x squared, e to the minus y squared.
That's fine. I just was wondering the dependence of sigma of k on k itself, and you have a k squared.
We don't know how it depends on this, and it doesn't matter. K is a label and sigma is a dummy variable of integration. So the K just tells you the label. It just says which variable I'm calling. So set K equal to 137. I'm looking at the variable of integration, sigma 137. I do the integral, that's just a number. That's just a variable, call it X, call it Y, call it Z. It's a complex number. I do that integral over sigma 137, and I get a number that depends on the number 137, and it depends on R naught.
Right.
And it's got, so did I answer your question? Yeah, good, thanks. All right, any other questions about this? Great.
Yeah, great. Did we get V from?
Where did we get V from? We got V from the factors that were in the functional integral. So here, let me choose a color so you can see it.
Oh, I see.
See this V over here?
Yeah, no, it's-
That came, where did that V came from? Well, that's why I took great pains to tell you about the density of states in K space and all of that. It came from that V there. Okay. All right. So, okay, so that's good. All right. So that's what Z sigma is. So then it is clear that now I can ask what is ZS? And that's just going to be the integral ds prime e to the minus 1 over 2v, the sum from naught is less than k is less than lambda over L, R naught plus k squared times SL prime of k squared. Okay, so what we've got now is we have our partition function. Our Z is ZS times Z sigma. We're trying to integrate out the short wavelength degrees of freedom. We're not trying to integrate out the long wavelength degrees of freedom, because what we want to look at is the recursion relation for the coefficients in the effective Hamiltonian. So what we're going to do is we do this integral. So we do this integral, which I just did. And now that I've got that, here's my problem. My original partition function has naught is less than k is less than lambda. But if you look at our expression for z sigma, what I have left, this goes between naught is less than k is less than lambda over L. It has a different range of k. So we can't, as I explained before, we can't just compare them. So the next step that we need to do is we need to do the renormalization step. We need to rescale space. And the way we're going to do that is we're going to say that K at scale L is just the original K times the scaling factor L. And if I do that, then what that will mean is that after I've done a renormalization group transformation, naught is going to be less than KL is going to be less than lambda. So I want to change variables from K to this variable KL. Okay, so we're going to do that transformation. So now it becomes that we have to remember, as I told you in the introduction, we have to remember that the dimensions of the field itself are 1 minus d over 2. We worked that out last time. So what that means is that SL as a function of KL, that's going to be a new field. It's going to be proportional to the field SL prime of K, because that's where it came from, but we're going to see how it rescales when I do the rescaling of space. And it's going to scale in a way that's non-trivial because it has non-trivial dimensions in space, non-trivial dimensions on L. So I'm going to call, there's going to be a coefficient of, there's going to be a coefficient that comes in here, and I'm going to call that coefficient Z to the minus 1. Okay, they have to be proportional. It's still the spin variable, but we're just rescaling it. So this is a factor to be determined. We need to work out what is that number, and it's to be determined by requiring that the coefficient of grad SL squared is equal to 1/2. So that's going to be the condition that sets the renormalization scale. So I have 2 more minutes. Let me just go a little bit further down this road. So therefore, now what our partition function looks like after I've done this rescaling, it's going to depend on the coupling constant R0. It's going to be a functional integral over these coarse-grained degrees of freedom. And I'm just going to write it down and let you take a look at this. So we're going to have e to the minus 1/2. Now, the new variable, KL, is going to go from 0 to lambda, just as we want. So this is going to be dk of 2 pi to the d. Then I have a factor L to the minus d, which came from the rescaling on the left-hand panel. Then I have R0 plus KL squared over L squared. Where does that come from? Well, that is because K is KL over L. And then my variable of integration is SL of KL, absolute value squared. And then it is multiplied by its renormalization factor, which is Z squared. So S prime is equal to Z times S. And so I've substituted that in. And so therefore, if I look at the coefficient of K squared, KL squared, that coefficient is the following. It's minus 1/2 L to the minus D plus 2 times Z squared, and that should equal minus 1/2. That's what we want to have happen. And so that means that this renormalization constant, Z, has to be L to the power 1 plus D over 2. This quantity is known as the wave function renormalization. And so what that means is that in these terms then, Zs of R0 is now equal to integral dsl e to the minus 1/2 integral from 0 to lambda dkl over 2 pi to the d. RL, which I'm going to write down what it is in a minute, KL squared times SL of KL absolute value squared. This is now in the same form as the original, and you can read off that RL is equal to L to the minus D Z squared times R naught, which is equal to L squared R naught. Okay, so all I did was I substituted from here, from this level into here, and I'd like you to check that before next lecture. Okay, so just one line of algebra. Okay, so that's the Gaussian theory. Okay, that's just using the part that you can exactly integrate. Okay, we haven't even talked about the interactions between the fluctuations. Okay, but so these manipulations though are elementary. They're just a series of steps, and you can do them exactly at Gaussian order. Okay, so next lecture, I will finish this for the first lecture of next week, lecture 10, lecture 19. We will go through I will now show you how we include the interaction terms in this way. Okay, so time to finish. So let me turn off Zoom.